It's February in Santa Barbara. Let's go teach a class. All right, so last class we talked about all the ways we could detect planets. We went through radial velocity, we went through the transit method, we talked about direct imaging, we talked about astrometry, we talked about transit timing variations, we talked about microlensing, what else? Astrometry? We already got that one. So there are a bunch of methods, but there's two that are far and above the most successful methods. Those are the radial velocity measurement, which is the first method that detected a planet, 51 PeG, in around 1995. So this is not, the first planet's barely older than you guys. It's a lot older than that. But the first detected planet. Then after that, that's discovered ballpark 1,000 planets. We know about 5,000 confirmed exoplanets. The other 4,000, almost all of those come from the transit method, mostly from a space mission called Kepler, which was launched in the early 2000s. We will go through all of that in the next class and show the planets we've discovered. But today we're going to cover the math behind the radial velocity and the transit method, and if we have time, a little bit of astrometry. So it's none of it's particularly complex math, but this is you'll see this stuff all the time. You'll see V sine I all the time, and understanding the math will let us understand what those measurements actually mean. So first we'll start off with the radial velocity method. So in the radial velocity method, and the two techniques we're going to talk today, I want to stress, the radial velocity method and the transit method, they are built around detecting the light from the star. It is very hard to detect the light from the planet. It's very faint. So what we do is look at the planet's effect on the star. So in the radial velocity method, you basically have a star at the center of your system, and you have a planet that's orbiting. It could be in a circular orbit, it could be an elliptical orbit, but it's some planet, orbiting around the star like this. As we studied before, the star and the planet have a barycenter, and so what actually happens is the star orbits its barycenter, and the planet orbits they both orbit this barycenter, okay? And so what that means is the planet causes a wobble in the star. And this wobble is from gravity, but it is detectable. And we detect it through the Doppler shift. So the Doppler shift is the change in wavelength divided by wavelength is going to be the velocity in the line of sight to you divided by the speed of light. So this is not relativistic. This is only valid for low speeds like you see in planets. And we're talking about walking speeds here, right? Like if you're on a fast jog, you're going to be at faster speeds than we're going to be talking about today pretty much. Okay, so this lambda here, this is the wavelength of interest. The way we usually do this is we use a spectrometer, and so we look at emission lines from the star, usually a particularly bright emission line. So this guy is going to be usually in the 400 to 800 nanometer range is where we want to do things. Okay, so in that 400 to 800 nanometer range, we can see what kind of change we're going to get. Again, I want to stress this is the line of sight velocity. Okay, that's moving towards you or away from you. If it's moving sideways, there's no Doppler shift. It has to be moving forward or away from you. So what we will see if we have a planet in a circular orbit is this planet will move around the star, that tugs on the star, and then there's some velocity that that you're going to get Vmax, and this is minus Vmax. And you're just going to have some periodic motion as a function of time around, around the star. Okay, so when do we reach Vmax? Vmax is, you can think of this as in two places. If you're looking at a system, now this is not face on, and you'll see why it's not face on. This needs to be tipped. So it might be a circular orbit, but it's tipped to us, and we'll talk about that. It's called inclination in a minute. So this maximum velocity is going to be achieved like right here. Right? That's when it's moving away from you or it's moving towards you. That's when you're going to see the maximum velocity. When it's here, you know, it only has transverse velocity, and so you're not going to get any signal there. All right. So what is the Vmax of the that we should expect? So for the Sun and Earth, you can just write down that Vmax is equal to 2 pi a. That's the semi-major axis of the Earth, one astronomical unit, divided by the period. So this is assuming a circular orbit, right? This is 2 pi a is the circumference of the orbit, and p is the period of the orbit, 1 year, 1 AU. So in this case, we can write down that A naught, or A Earth, is going to be mass of the Earth divided by the total mass of the system, which you can approximate to the mass of the Sun to very high accuracy, times the semi-major axis. And we know from our previous work that this ratio, the mass of the Earth to the mass of the total, is like 3 times 10 to the minus 6. So the Earth is, obviously a very small fraction of the mass of the star. Okay, so when we can work that out. So using this A, we can plug it in here. This is 1 year. This is A naught. With that, we can plug in for Vmax. And it's going to be 2 pi 3 times 10 to the minus 6 AU divided by 1 year is going to be equal to 9 centimeters per second. This is also, you could rewrite that as 0.3 kilometers per hour. This is crawling pace. Like, they're babies who can move faster than this. So the Earth's pull on the Sun is pretty weak. It's 9 centimeters per second is the maximum velocity you achieve, when the Earth is here in its orbit. So this is tough. This is a really hard measurement. Just to show you how tough, we can look at what we would typically get for a high-quality spectrograph. So we can write down here that we can figure out what delta lambda is, that wavelength shift. It's going to be equal to the wavelength times Vmax over c. This is the maximum wavelength shift you could get. That's going to be, so we're going to say 500 nanometers. That's smack dab in the visible, where our spectrographs tend to work and where there is a lot of good lines to do this with for solar type stars. And you get 9 times 10 to the minus 2 meters per second divided by 3. That's the Vmax that we calculated over there. 9 centimeters per second divided by the speed of light, which is big, 3 times 10 to the 8 meters per second. So that means that this total shift here is only 1.5 times 10 to the minus 7 nanometers. So that is, a nanometer is 10 to the minus 9. That's 10 to the minus 16 meters. That's a very small number. And if you know, an atomic spacing is usually on the order of, the atomic spacing is on the order of an angstrom, which is 10 to the minus 10 meters. So this is much smaller than the distance between atoms. And to make it even more impressive, we have spectrographs which divide light up into tiny little bins so you can measure high-resolution spectra of objects. A really good high-resolution spectrograph might have this R factor be equal to about 300,000, 3 times 10 to the 5. Okay? And that, if you figure out at 500 nanometers, that means that delta lambda is on the order of 10 to the minus 3. So you want to compare this number. This is how good our spectrographs can resolve a spectral line, about 10 to the minus 3 nanometers. But we need 10 to the minus 7. All right, so this is really hard. And this is going to be, we're going to spend a lot of time next class talking about how to do this. And the hint is that you can centroid a line much better than than you would get. How do I say this better? You can centroid a line if it has high signal to noise to much higher accuracy than like the width of the line that you're looking at. So essentially we've got a Gaussian that looks like that, and we want to find its center. So you can't, it's not the width of the Gaussian that determines how well you can find the center. It's like what your signal to noise of all the points leading up and down the Gaussian is. So if you have enough signal to noise, you can do this. You can do something. Turns out no one's ever demonstrated 9 centimeters per second yet. We've demonstrated the best spectrographs are about half a meter per second, about 50. We're trying to get down to this level because we want to see Earths. But the trick we mostly use is we just look at bigger planets. That gives us a bigger signal. So we can't see these things. We're trying. There's a lot. We'll talk next class about all the things that can go into messing up your radial velocity precision. And there's it's multitude. When you start pushing down, you're dealing with the star itself isn't quiet. There's sunspots, there's stellar granulation, there's atmospheric effects, there's calibration effects. It starts getting really hard. So about half a meter per second, about 50 cm per second, is sort of like state of the art for instruments like HARPs and that are sort of designed for this from the ground up. Question?
Yeah, just to be clear, the max velocity, that's the velocity of your star.
Yes.
Moving, yeah. That's
the maximum velocity the star moves in your line of sight. If it is perfectly edge-on oriented to you and at the right part of its phase. It's like the best case. Okay. So given all this stuff, and I will show next class how we actually do it because it's quite hard. We actually can talk about how to use the data. So let's just assume that we're able to do this. And again, this is going to be a lot easier for Jupiter mass planets. You're going to have many meters per second of signal from these Jupiters. And so it's much easier to find the big planets. But what we want to do is we want to measure the planet's mass. How do we measure planet mass from this RV technique? So we can go back to our equation, Vmax equals 2 pi a star over p. Okay, so we know that a star is going to be mp over m tot times the semi-major axis again. And then we also know from Kepler, our old friend Kepler, that we can write down the relationship between period and semi-major axis. So the period squared equals 4 pi squared semi-major axis cubed over g m tot. All right, so if we put those together into this Vmax equation, we can then, well, first let's go and write down what A star is. A star equals mp over m tot. That's just here, okay? And then we can put in A from here, from Kepler. We're just going to solve Kepler's equation for A. And that gives us g m tot over 4 pi squared p squared to the 1/3. All right, so that's the acceleration of the star, the semi-major axis distance of the star, not acceleration. Okay, then we can simplify that a little bit to be mass of the planet g over 4 pi squared m tot squared p squared to the 1/3. We just move the m tot inside there. All right, then we can go back to our Vmax equation. And we can say Vmax equals 2 pi over P, mass of the planet, G over 4 pi squared m squared tote P squared to the 1/3 power. All right, so now we can now solve this equation for MP, the mass of the planet, in terms of our other variables. And so when we do that, we get that the mass of the planet is equal to 2 pi g to the minus 1/3 power times m tote to the 2/3 power times period to the 1/3 power times Vmax. All right, so that's the mass of our planet. So we know in this equation, we know pi, because we know about circles, we know g, we know m tote. That, to get m tote is actually not trivial. You have to basically characterize the star. So basically, we have to use our knowledge of stellar astrophysics to figure out what the star's mass is. And so that is an unknown in this, right? If you, even if you measure everything super precisely, if you don't get the mass of the star right, you're going to mess up this calculation. So it turns out for main sequence stars, we're pretty good at this. This is usually not, I think, the dominant error. The dominant error is this term here, which is essentially the stuff you have to measure from RV. So that period times Vmax. So if you actually take this data, right, on a star, you're going to get this, sine wavy behavior, and it's going to have time. And from this, you can measure essentially Vmax. That's going to be the height of this is half the height of the sine wave here. And then the period you can just get by by measuring the time it takes for it to go all the way around. So when you get both of these out from this radial velocity curve. So if you know the mass of the star and you measure this radial velocity curve, you nail the mass of the planet. And that it's a pretty accurate measurement. We'll show some real data next time. Okay, so this makes sense for a circular orbit. But we also have to, but most things are not in circular orbits. Most things are in elliptical orbits, as we talked earlier. I should say that a circular orbit is a special case of an elliptical orbit, right? As we've talked about before. So let's go and see how this gets modified when we have a elliptical orbit. So here we have to do some geometry because we have the inclination of the system matters, and we'll go through that. So if you remember when we did our elliptical orbits, we wrote down that a of 1 plus eccentricity squared over 1 plus eccentricity cosine nu. This is the equation for the position, for the distance of the planet to the star as a function of the eccentricity, how squished the ellipse is, and this nu, which is we call that the true anomaly. So the true anomaly is basically tells you where in your orbit you are. Okay, so this was what we worked with when we did celestial mechanics and worked it out. In this case, we're going to do a simplification. So we're going to imagine that we're the observer here, and we're looking at a system. And we're looking on the plane of the sky, which is this line right here. And on the plane of the sky, the orbit is going to make some ellipse. And we're going to call this z equals 0, some 0 point here. And the distance from the center of the orbit to where the planet is, that's the r that we wrote down in this equation here, right? R is the distance to the planet as it goes around its orbit. This is positive z farther away from you. So if we have this case where we're observing over here, we can write down this distance z as r times sine of I times sine of omega plus nu. Just go like that. Okay, so this is the inclination. This is, omega is the, what's the word? Oh yeah, it's the argument of periastron. And this nu is just the true anomaly again. So the argument of periastron is, this is just setting a 0 point in your measurement, right? You have to have a point where the orbit, say, crosses, you know, the plane in here or something. You have to define it somehow. And here we're just defining it as the argument of periastron. It's essentially a constant. Doesn't get involved in this whole thing too much. This is just the position where you are in the orbit. This, you know, different as you change v from 0 to 2 pi, you move around the orbit. And then the inclination is the thing that really matters. So we've kind of transformed into a coordinate system where the most important thing is characterized by this one variable, I, the inclination. So inclination is set so that if you have a face-on orbit, inclination is 0. So that means you're looking at a system like you're looking at a pie straight on, right? You're looking, you have, it's the orbit might be circular, but or elliptical, but it's orbiting completely in the plane here. There's no tip, so your system is all in this z equals 0 plane. That's inclination of 0. That is the worst case for RV. Right? If you have a face-on system, you get no RV signal. Whereas if you have an edge-on system, if I equals 90 degrees, it'll be tipped over. Then you get the biggest possible RV signal because the thing is moving directly towards you. Yep.
If I remember correctly from when we did orbital mechanics before,
yep.
Inclination was the distance from the reference direction, right?
Yep.
When we did the solar system, we did it plane on.
Yeah.
So
in this case, it's defined. So for
different inclination.
It is it's inclination relative to to the plane of the sky essentially. So it's just defined so that something face on is inclination of 0. All right. So as this planet orbits and you watch, it's going to move on here, right? It moves along this orbit. As a function of time, it takes the period p to go around it. There are a couple points here. There's the point where your closest approach, right? That's periastron. Periastron, and then this point over here where you're farthest away, that's apastron. The main thing that matters though is that this inclination term modifies all your RV data. So whenever people report an RV measurement, they always report the maximum mass if it was edge on, right? So there's always this sine I factor. So when you read a mass, it says, oh, this is 8 Jupiter masses m sine I. That'll mean that if it was edge on, it'd be 8 Jupiter masses. But if it's but if it was like really tipped, it could be a brown dwarf. And you can't tell the difference unless you have some other data that helps you figure out the inclination of the system. Like maybe you could see a debris disk, or maybe a planet transits, which tells you it's edge on. So you need other information or else the mass you get from RV is just a maximum mass. All right. So now let's talk about the what is this. So what is the velocity in the z component headed towards you as a function of time for an elliptical orbit? This is more complicated than the circular case, and we're going to skip the math and just write down the result. It's just geometry about projecting this ellipse. So it's nothing crazy. It's just we're going to skip it for the sake of time. So Vz is going to be equal to this factor k, which we'll say in a second, times cosine omega plus nu. That's just our term for the for this from here, and then we get eccentricity cosine of omega. So this is a factor that again, the cosine omega is basically a constant. This tells you where you are in the orbit. So this is a function of this of nu, the true anomaly. Okay, so the real important thing is this k, this prefactor. So k is going to be equal to 2 pi g over the period to the 1/3 power times mass of the planet sine I. See, it always comes in as m sine I times m tot to the 2/3 power times 1 over 1 minus e squared to the 1/2. So this k factor is called the RV semi-amplitude. So that's essentially, we can plot what this looks like. So for eccentricity equals 0, you just get k equals v max that we derived before for, this is a circular orbit. For e is not equal to 0, we get some RV curve that that has a little bit of a different shape. It's not a perfect, it doesn't have like perfect symmetry. It's going to be, it's going to have a weird height. It's not going to be centered around 0, and you get like, the total height is 2k. That's why we call it the semi-amplitude, because it's 1/2 the total v max minus to v max plus. And then you'll get different peaks here. So this is periastron, and this dip is apastron. And so that is that's basically what it looks like. So you get these curves that are non-symmetric around the 0. Yeah.
How would you find the argument of periastron and the true anomaly?
Yeah, so the argument of periastron is just you measure the star's position on the sky, and then you're going to assume that the argument of periastron is like probably north in your, depends exactly how you're going to do it, but you're going to most likely make an assumption that like you're going to say, okay, 0 is north, the direction north from human north, right? Like on our sky, north, we'll set that as 0. And then the argument is just going to be the position angle, basically. It tells you where you are around that circle. Okay, so what makes the planets easier to detect? So if we look at this equation, this is all the hard part of our RV measurement. This tells us how big our signal is. So this is something we're going to look at a lot. Okay, so first off, if you have you've got a period here in the denominator, but only to the 1/3 power. But this means that smaller periods make it easier to detect. There's a second argument here too, that you have to have a lot of patience for doing this. If you're looking at a Jupiter-like planet and you've got an orbit that takes 5 years, or Saturn at 10 years or something, right? You have to, if you want to get it, you really need to see the whole orbit to really be sure of what you're seeing, or at least most of a full orbit. So you have to be patient to really nail this down. And so longer planets are hard just because humans get bored of looking at it, and we've only been doing this for about 20 years. So we have, so smaller periods make it easier. So that's one thing we look for. Obviously, planet mass shows up in the numerator here linearly. So planet mass scales the signal directly, right? You have if you have a 2 Earth mass planet, it's going to have 2 times the signal. It's just, if you have a 300 Earth mass planet like Jupiter, you get 300 times the signal. It's much easier to see. So that's so planet mass is this is essentially, we're characterizing what we call the biases of this technique, what it's good at, what it's not good at. Another one that's not obvious is this m tot in the denominator, right? So this is the mass of the star, basically. So if the star is less massive, it gets pulled around more by gravity, and you get a bigger signal. So this works better around smaller stars. Unfortunately, there is a caveat there. Smaller stars like M dwarfs don't have as good spectral features to do this work in. So we actually do this more on like sun-like stars than on the really low mass stars, because you only get a factor of 3 from the lower, an M star is still about 1/3 of a solar mass, but its atmosphere doesn't have a lot of nice lines to do this this work in. Yeah, question?
Yeah, I think I missed it. What was the argument of Digression?
That's this. It's basically telling you, the angle of your closest approach to the star, and so you could. We work in position angle, which is reference to north, but I think this argument of periastron probably is essentially the nu you need to get to at periastron, at closest approach. That's probably defined as, now that I think about it more, that's probably defined as this argument of periastron, because that's literally what it's called. So it's probably the angle that gives you the closest approach. And then that is set at 0. And then so 180 degrees, if the true anomaly was 180 degrees, that would be apastron. I think we finally got it right. Yeah.
Do we get like a large distribution of what K could be with like the mass of stars? Do we like count all of those, or are we usually pretty accurate?
We're pretty good at the mass of stars. Almost every star we're looking at is somewhere between like a half a solar mass and about 3 solar masses. This is a weird thing about exoplanet astronomy, is that the lifetime and the brightness of a star goes up super fast as a function of mass. It's like luminosity goes like mass to the 3rd power or something. So you get so if you get much more than 3 solar masses, the stars are like super crazy hot, and they only last like 100 million years or something. And then by the time you get to like 20 solar masses, the star might last 5 million years, 10 million years. It's like really fast. And since we're mostly looking at planets that take a little while to form, we're looking at stars that have atmospheres that produce spectral lines that we can work with for this RV technique. It can't be too hot of a star, because then you fully ionize all the elements and you don't get all these nice lines. So we're not looking at O stars or B stars. We're mostly looking at A stars, which go up to only about 3 solar masses. So that's kind of like the high end of what we're looking at with RV. The low end's like half a solar mass or so, maybe a third. If we go into the infrared, you can go down to the M stars, which are like a third of solar mass. So it's not a huge range, and over those ranges, we're pretty good at figuring out what stars' masses are. There can be we have some other things in our toolbox to help figure out mass, like there's the technique there's astrometry stuff you can do. There's parallax to get distances. So we're actually pretty good at that stuff. So we know this pretty well. This is the one. The inclination is really we often don't know that inclination. The period is usually pretty easy to measure, and the eccentricity is not so hard. So, we kind of can, as long as we have enough signal to noise, we can pretty much do this and get a decent answer out. Okay, one more thing I didn't. So smaller mass changed it. Also, the eccentricity comes in here. So higher eccentricity makes it easier to find, because you peak up more here you get bigger peaks from eccentricity, because basically, if you think about an eccentric orbit that you're sweeping out equal area for equal time from Kepler's law, if you have a very eccentric orbit, you come in and you have you have like this really close pass to the star, and your Vmax as you're moving through close to the star can be real high, and that peaks this up and makes it easier to detect. So this is kind of the bread and butter that we use. There's a lot of other techniques that we use for exoplanet astronomy, but RV is kind of our backup. It's our main tool to like really to follow things up. So if we detect like a planet around a star with the direct imaging technique, which is what I do, the first thing we'll do is go and try to get some RV data on it, and then we'll take that. And so if we get our direct imaging data, we'll go and get some RV, or ask people who may have already taken RV on it but not published it. We'll get that RV data in there, and then we'll go to Gaia and we'll get the astrometry data, and then we'll take all of those things. We'll take basically every piece of information we know about the planet and the star, and we'll throw it into a complex code that does like a Bayesian inference on the orbit and takes all the data into account with hopefully reasonable priors, and spits out sort of a most likely system that we get. So we did that in a paper with our MEC instrument a couple years ago. So if we have time at the end of the class, I'll show us, not this class, but at the end of the quarter, I'll show some of our results where we did this one on real data. And in that one, we did it with only 1 point. We measured the star right there, and we were like, oh, that's good enough. And then we threw it into the code, because we didn't want to wait for a year and come back and measure it a little bit. I think we actually did maybe we had 2 years of data on it. It's usually good to have not more than one. When you have astrometry, you can do it, and the code will show you that, you know, like there'll be like a bajillion different orbits that all pass through your one point, and then so you're looking at this whole sea of possibilities, and you have to, and that kind of bounds the possibilities. But when you have multiple points, you constrain your data to have to pass through multiple points. It's much easier to get a reliable answer. All right, any more questions on the RV technique before we move on to transits? Okay, transits. All right, so the transits are, we talked about a couple times. We see them in the solar system when Mercury and Venus pass in front of the sun. And you know, but that doesn't happen every year, right? Every time Venus and Mercury pass in front of the sun, there isn't a transit. And that's because the system is not perfectly, Mercury and Earth and Venus are not in a perfect circular orbit so that every time it passes through, there's wobble in each of those orbits, and they kind of go up and down, and so they don't always eclipse. April 8th there's a big eclipse, which is a transit of the moon in front of the sun. That's going to be visible from like Texas up to like Maine. It's a huge thing. I was trying to figure out if I could go. I've been to one eclipse before, the 2018 eclipse. We had a conference in Idaho, and I went to it. And you know, I'm pretty jaded. Like, I'm an astronomer. I've done hundreds of observing nights at the biggest telescopes in the world. I've seen a lot of cool stuff, and I'm like, I've looked through a lot of amateur telescopes and been like, oh yeah, look, there's a little red spot. It's Mars. It's okay. Yeah, it's so cool. Although I will say, if you're looking through a telescope, look at Saturn. That one's pretty awesome on a good night. But I was pretty jaded, and then I went to that eclipse, and I was like, had a religious experience. I was like, oh my God, the mysteries of the universe. Like, it is, a total solar eclipse is really like nothing else. And my in-laws go to, they've been to like 10 eclipses. They go to like every eclipse. And now, I thought it was insane beforehand, and now I was like, yeah, no, I kind of get it now. It was pretty epic. So if you have a chance to get out and see a total eclipse, it's definitely worth it. All right, transits. Okay, so the transit, you've got a star, okay, and you've got a planet. And this planet is essentially moving as a function of time across the star. And so what we're going to measure here is the flux of the star, right? Where the planet is 10 to the 9th time or more times fainter. No contribution from the planet usually in this case. And then we're measuring this flux F as a function of time. Okay, so we can essentially draw a curve that looks like this for the flux. And so, you know, out here, this is just the star's intrinsic brightness. This point right here, this was what we call ingress. This is as the planet crosses the limb of the star. Then we have you know, the mid-transit point right here, where we're in the center of the transit. This point here where it comes out, this is called egress. And then we've got the total depth of this dip, which we'll call delta F, the change in flux. And then there's another important thing, which is the time here, where we'll call that delta T. That's the transit duration. Okay, transit duration. Okay, so this is the simple picture of what we're seeing. There can be some more complicated physics going on. In reality, that you cannot see like that this comes down a little more than it probably should. One of the reasons this is limb darkening. So if you look at a picture of the sun, it looks like it's fainter at the edges than on the center. This is a phenomenon called limb darkening that we don't have real time to get into, but that is something you have to take into account. It's essentially the brightness profile of the sun. It's not a flat illuminated disk. It actually is dimmer at the edges. So that comes in to this equation. But essentially, this is a very simple technique mathematically. Like, this only happens if the system is like really well aligned. We'll talk about the math of that, but this is like, one of the advantages here is this is one of the simplest measurements. So you can write down that the change in flux is essentially just geometric. It's just pi r planet squared over pi r star squared, which is rp squared over r star squared. Okay, so for the Earth to the Sun, this is about 10 to the minus 4. So instantly we're in like, part in 10,000, yeah, maybe we can do that, like that. This starts becoming, this is the advantage of this technique, is that the radius of the Earth, right, is not, it's scaling differently from mass, right? It's mass to the 1/3 power. So you're getting, your ratio here is more favorable. So you only have to measure the change in the brightness of the sun to a part in 10 to the minus 4 to see an Earth. And this turns out to be difficult, but possible. We'll show in next class, the Kepler mission has actually measured some objects down to like about Mars sized. It's actually gotten smaller than you can actually get down with space missions down to like part in 10 to the minus 4. And we're going to do this. This is homework 4. We're going to be downloading some real Kepler data and fitting those transits. And so that's we'll go over that either next class or the class after. We'll go through the homework because again, that homework 4 is the big homework with that's worth more. So we'll spend some time on it in class, and we'll get Skylar to also do it in section. Okay, so looking at this, there's one thing to note here is that you have to know the radius of the star, right? That's the whole. If you want to get that's your source of error. How accurately do you know the radius of the star? It may be if you had a perfect measurement with high signal noise, you might be limited by this. But again, for most of the stars we're interested in, we have a pretty good idea of what we want to do for of what the radius of the star is. So that's not such a big deal. We'll talk about. Let's talk about some of the noise sources here. We'll go into this in a lot more detail, but stars change brightness continuously. So if you look at there are stars called variable stars that have, there's a lot of different kinds of variable stars that have really like periodic motion and other things, but even a star like the sun, which is not a variable star, you have sunspots coming across that are bigger than this effect, and then you can have solar flares, which can dramatically change the brightness of the star. The M stars we look at, these low mass stars, they flare continuously. I don't think I've ever looked at one and had it not flare. Like they're just shooting, their brightness is just changing like a couple magnitudes like constantly. They're really annoying. So there are a lot of things that go into this just from the star and then also from the instrument. Like you need a very stable platform. If you're trying to do this from the ground, you're looking through the atmosphere. The atmosphere is messing everything up and it limits your precision, to a good bit less than 10 to the minus 4. So also the brightness of the star matters. Like the brighter the star, the more photons you get, the better you can measure this ratio. So we'll talk about real world measurements from missions like Kepler and now from JWST. And the JWST measurements are actually giving us some really interesting information about planetary atmospheres, which we'll cover later. Okay, so the one thing I want to talk about here more is the transit probability. It's pretty simple, but the idea essentially is that if you're looking at a system, you've got, you could have a star here and you could have a planet, but this planet could be in an edge on orbit, it could be on a face on orbit, it could be anywhere in between. You're essentially if you don't know what inclination is that it's at, the star you can essentially trace out a sphere around the star, and in order to actually see it, it has to actually transit the star, and so it has to essentially, the orbit has to be contained in a band so that the planet will actually get in front of the star. And this is not a super likely occurrence. If we write it down like this, then the width of this band is essentially 2 times the radius of the star, right? So it's the diameter, just the geometric diameter of the star. So then the transit probability, put it over here. So that transit probability is just going to be, the probability is the area of that band over the area of the sphere with, this essentially is A, the semi-major axis of the star. And so when you do that, you just get 2 pi A times 2 pi r squared over 4 pi A squared, and you get basically r star over A. So this is the transit probability. So the radius of the star divided by the orbit that the planet's in. This is this can have a wide range of values. But a rough guess, a rough order of magnitude here is 1%. So if you look at a random system, the chance that it transits is on the order of 1%, depending on the exact how far away the planet and the star are. This is this actually is important because it tells you how far away you have to look to find a planet that transits. So if you wanted to find the nearest transiting M dwarf, the nearest transiting planet around an M dwarf, which are the easiest ones to measure the atmosphere, which we'll talk about in a minute, you need to essentially go out, measure, it's probably about the 100th star. And there's a system called TRAPPIST-1, which is about 10, I forget if it's 10 light years or 10 parsecs. I think it's, but it's essentially, I think it's probably 10 light years. So it's, so TRAPPIST turns out to be, it has like 6 planets transiting it, and it happens to have the right orientation. And if you check, it's like the 100th closest M dwarf, right? So the math kind of works out. But these systems are really important because they let you, the transiting systems give you a lot of information. Like when we did that mass radius relation stuff earlier for the planetary structure, you need both RV and transit in order to nail down the density of the planet and do that structure work. So these systems that transit are special, and that's why we use them. Kepler took a different approach. The reason why Kepler was, what Kepler did was it didn't look at the nearest planets, the nearest stars, because it had a limited field of view on the telescope. It could only look at a very few stars. If it looked, it would have to go like one at a time, basically. But they didn't want to do that. So what Kepler did was actually look close to the galactic center, so in the plane of the disk, where there's just a ton of stars. So most of the planets in Kepler are actually something like a kiloparsec away. They're really far, 3,000 light years or something. And since they're so far away, we can still do the transit method because we're so sensitive, but we can't follow them up with other techniques because the host stars are pretty dim and the angular separation is really small. So Kepler is really good for exoplanet demographics, which we'll talk about in a later lecture, but not so good at following up nearby systems of interest. Okay, the final thing about the exoplanet transits that I want to talk about is how we use it for spectroscopy. So up to now, the RV technique, does not tell us anything about the planet itself, and it especially doesn't tell us about the atmosphere of the planet, which is where we're really interested. If we want to look for life, if we want to look for things out of chemical equilibrium, we're going to look for we need to look at the atmosphere. So when you have this transiting system, you actually, you have some rocky core of a planet, but then there's going to be but the planet has some atmosphere, RATM. So you've got the RP for the planet, but you also have this RATM for the atmosphere. So when this goes across, some of the light, the light that's blocked by this dense core is obviously going to just be the same, but some of the light is going to go through the atmosphere and come to you and get processed by the atmosphere. And so we can write down how that works. So we can say delta F, the change in flux from the atmosphere over F is going to be delta F total minus delta F planet over F, which with some geometry, we're just going to get pi r squared atmosphere minus pi rp squared over pi r planet squared. So that simplifies down to the radius of the atmosphere squared minus the radius of the planet, rp squared over r star squared. So that's the extra change in flux from basically rp. You know, this is how much of is getting processed by the atmosphere. The annoying thing is that this is small. So for Earth, we have basically, you have to worry about optical depth here, but I won't go into it too much. But the Earth is like 6,000 kilometers. The atmosphere is about 10 scale height. So the amount of flux that's getting processed. So this is you've got a small signal, which is the transit, and then the atmosphere is an even smaller signal riding on top of the signal from the atmosphere. But basically, what happens is that our atmosphere is a function of wavelength. Basically, if you have a measurement at just one wavelength, you can't tell anything about the radius of the planet because you just get a radius. It's what it is. You have no more data. But if you can get this transit curve at a bunch of different wavelengths, you can then look at the radius as a function of wavelength with this equation. And that's essentially what you're measuring. So you're measuring the wavelength as at different wavelengths. And so say you have a strong absorption feature like a lot of methane in your atmosphere. Then that means that at certain wavelengths, the methane will absorb better, and that means the planet will look bigger because the optical depth is higher in the atmosphere. And so you get a dip in your, if you plot the total, this delta F term as a function of wavelength, if there's an absorption band, the planet will look bigger, you'll get a bigger dip in your flux. And so you can extract a crude measure of spectroscopy using this atmospheric transit technique. And that is what the James Webb Space Telescope is doing on a lot of these nearby systems like the TRAPPIST systems. And unfortunately, it looks like everything is a goddamn cue ball. Like I've staked a lot of my career on looking at M-dwarf atmospheres around nearby with this new 30-meter telescope that we're hoping to build one day. Not looking amazing at the moment, but fingers crossed. But we need these M-dwarfs to actually have atmospheres. Unfortunately, when JWST has looked, it's consistent with a flat cue ball. So it could be two things. One, it could be they don't have any atmosphere and they're just a rock. Or it could be that they're cloudy and the clouds essentially mask any atmospheric signatures. It's probably cloudy. We've got some other data that shows that like everything is cloudy. And so when you're cloudy, like the clouds are high, you basically see our cloud deck. You don't see any of this atmosphere stuff. So it can be kind of annoying. So a lot of research to be done in that field as we go forward. Okay, questions on transits. What time is it? Oh, we got a little more time. Okay, so let's move on to astrometry since we've got a little time left. So this won't take particularly long. Okay, so this is, again, one of the oldest techniques for detecting planets. We're looking at the orbits of Neptune, of Uranus to see Neptune. That's the kind of thing we're doing here. We're basically looking at the motion of stars and using that to determine if there's a planet. So what we essentially do is we look at a field of stars. Many of these stars are background stars that are quite distant and basically don't move much. They kind of stay in place. But then if you look really carefully, some of these stars will move, right? So you have a bunch of stars. You use most of the stars as a fixed reference, and you say, okay, these stars are either they have some proper motion that we'll take into account, or they're fixed, and that's our reference frame. And then we can look at this one star, and then you'll see in this fixed frame, this one star will move. Now, every star does move in the sky because of parallax. The Earth goes around the sun, and that causes some wobble in any nearby stars. We're already assuming we're taking that out. Yeah, question?
Is there like, do you have to assume there's like a specific distance between them in order to like approximate that they're a background, or are you just able to assume?
You can look at them and see that they don't move. But what we can also do is use, there have been some space missions like Gaia especially, which we'll talk about. Gaia has measured the position of like every bright star in the sky to a pretty accurate position. So because of this annual parallax modulation, we can tell what's far away when things have low parallax. And so we have a decent idea of what's going on. Everything in the galaxy is going to move at some level. When we want things that are truly fixed, we look at distant quasars that are, billions of light years away, and that's what fixes our inertial reference frame of all of our astronomical observations. But that is we're getting in the weeds there. Okay, any other questions? All right, so the amount that you're moving here, is the amount on the sky, this distance that you're going to move is going to be something like, again, the same thing as before, where you're going to have the mass of the planet over the mass of the star times A. This is just the Barry Center that we've done a million times. The interesting thing here is that this goes in as the orbit of the planet comes in here. So this is actually sensitive to large separation planets, which is something that most of our other techniques are very bad at. So for the transit technique, that transit probability, the farther the planet is from the star, the lower the transit probability, and the longer the period. If you have one transit every 50 years, like we're not going to see it. Like it's not happening. So transit's great at finding things close in. RV is good at sort of middle distances up to it depends how patient you are to wait for the orbit to close. This technique is actually sensitive to large separation planets, like hundreds of AU, which is interesting and is a region that a lot of other techniques are not. And interestingly, it also works face on or edge on. If you're face on, that's the star is going to move like that, right? But if you're edge on, the star is going to move like this. And so you get motion, unlike the V sine I you get from RV, you face on or edge on, you still get a signal here. So one of the issues, of course, is that the motion is limited from Kepler's law. The amount of motion depends on the period, right? So if P is too long, you're essentially limited by the duration of the mission. So ESA launched this awesome mission, Gaia, that's measuring super precisely the positions of all these things in the sky. But spacecraft lasts, 10 years? If everything goes well. NASA usually says the mission duration is 5 years required, and their goal is to hit 10. JWST because the Europeans did a really good job getting it into the right orbit, it theoretically has enough fuel for like 20 years, but that doesn't mean all of its components will last 20 years. So the length of your mission sets a baseline on this that can also be an issue. And then, so this is a really interesting technique. As Gaia gets more baseline, it's going to start popping out a lot more of these planets. I will say that the acceleration here is going to be, it depends on the mass of the planet and the semi-major axis here. So you do have a degeneracy in this measurement. So you could have a small planet at small a, or you could have a large planet at large a. And so if you only have part of the orbit, so basically if you measure it from here to here over, say, 2 years, right, you'll essentially say that there's an acceleration vector here. And from that, you could say, oh yeah, this is an accelerating planet, but you have this degeneracy. You don't know if it's a small planet close in or a large planet that's far out. And to break that degeneracy, you have to watch the whole orbit essentially, or a big fraction of the orbit to break it. So we've actually used this to our advantage for exoplanet detection. So Tim Brandt did this analysis of the Gaia-Hipparcos catalog. Gaia is the mission up now that's looking at all the positions. Hipparcos was a mission about 25 years ago that did the same thing for a couple of years. And so what Tim did was took the data from Hipparcos on like the 200,000 brightest stars in the sky, found those same stars in Gaia, did a whole bunch of statistical work to normalize the data sets, and then linked them together and used that 25-year baseline to help find these planets in these much longer orbits. So what that gave us the Gaia-Hipparcos catalog, and what that catalog did was tell us whether its stars were accelerating. And so we could basically look at how many sigma of acceleration each star did. And so instead of having to look at every one of the 200,000 stars, brightest stars in the sky, we could focus on the ones where we had, where there was some anomalous acceleration. And that was a hint of where to look for the planet. And that worked really quite well, although we see this every time. When we look at a new one of these things, we either see nothing, which probably means either there's a data fluctuation or it's a small planet in a small angle, or we see like an M dwarf that's far away, that like a close binary. So there's a really massive like M dwarf there when we didn't. So we see this in practice all the time, but it's still a much more efficient method of selecting targets than a lot of our previous methods. Okay, did I see a question? All right, that will wrap up our math section. So today we're done with math. So the next class we're going to do, I think what we'll do is next class we're going to go into all the observational phenomenology of this. That's actually 2 lectures. So I may break it up with a little bit of a deep dive into the Jupyter notebooks that we're going to use for homework 4 and give some data on that. All right, thanks everybody, and we'll see you next class.